Hi everyone, hope you all are doing good. Today I'm back with another new video, that is sanity checks after synthesis. So if you haven't watched my previous video, you can go and click on this link above. So this is the link of a playlist where you will see all the videos related to synthesis that I have shared till date. So there you will find all the videos on the inputs required for synthesis and the stages of synthesis, the different types of synthesis, the outputs that are generated after synthesis. All these videos I have already generated. If you haven't yet watched these videos, please do watch out those videos first, then you come and watch this video, then only you can relate to this. So in this video, I'm going to discuss about the sanity checks that are performed after synthesis. So why do we need to perform sanity checks and what are sanity checks, we are going to discuss on this video. And also the sanity checks we are going to perform we are mentioning all the sanity checks for both logical synthesis as well as physical aware synthesis. So without any further delay, let's quickly get started. So first let us understand what are sanity checks. So sanity checks are basically, it performs to verify the correctness and the consistency of the inputs that are used during synthesis stage. And also these inputs will impact on the quality of netlist. So we can't compromise with the quality of netlist, since that will affect the full physical design synthesis, physical design stages, and it is just a wastage of time if the netlist is wrong. So we can't compromise there, so we have to make sure that the quality of netlist is good enough before we are handing over the netlist to the physical design team. So there are three major checks that we perform after synthesis. The first thing is we perform the sanity checks on libraries, sanity checks on SDC, and then at the end, if these two are clean, that time only we are going to see the sanity checks on the quality of netlist in terms of timing, power and area, so that we have a better quality of netlist. So first let's start with the library check. So we know that there are two types of library, logical library and physical library. So in library check, what we do actually, we basically, the tool verifies the consistency between both the libraries, physical and the logical library. And here I have mentioned the innoverse command. So for if you are working on innoverse, you can you can just write out this command, check design hyphen all. So it will report all the library checks related type library checks related reports. And then if you are performing on synopsis, that is synopsis toolset, that is ICC2 command, so for that you can use check library. So this will give a overall report. And if you want to perform separately for particularly for logical library, like why do we see that logical library check? So we do it on logical while we are performing on logical synthesis, or logical library check is actually performed for both the types of synthesis, logical synthesis as well as physical synthesis. So why do we check this logical library? Because if all the cells are present in the design, then it should also be present in the timing library. We need to check that whether those are present or not. So for that only we are performing this, we are writing out this command to check it, check design hyphen timing library. So make sure these comments are actually innoverse based. So these are not synopsis ICC2, these are all in innoverse based command that I have mentioned here. And we need to check physical library if we are performing physical aware synthesis. So we need to check that all the cells in the present in the design has a left view or not. We need to check that. So for that we have to perform check design hyphen physical library. So that's it about library check. Next we need to move with the SDC checks. So we know that SDC file means it's a constraint file where we mention all the constraints that the tool need to be aware of, and all the optimization directives also. So all these informations we give on the SDC file, and all the exceptions, timing exception informations, clock informations, everything is present on this SDC file. So this is one of the very important inputs for this synthesis and physical design. So we need to make sure that SDC file checks are properly done. So what we do basically, for Innovas and for ICC2, both Cadence and Synopsys toolset, we have a common or the same, we can say the same command, that is check timing, check underscore timing. If we run this command, we will see all the SDC related. If there are any errors, tool will show. If there are no errors, tool will report everything related to SDC. So more often we generally see SDC related issues like no clock issue or unconstrained endpoints or timing related issues. So these three types of issues mostly we see due to SDC incorrectness. So we need to make sure that SDC is properly correct. So first let us talk about this no clock violation. So why do we get this no clock violation? So in this check basically we ensure that all the required clocks should reach the sync points of the flop. That means we know that there will be a clock source, there will be a clock definition point, and from there all the flops that are present in the design, flops and the cells, everything should get, all the flops, especially all the flops clock pins should get proper proper clocks in the design. So if there is any clock definition missing in the SDC file, then only we may get no clock violation. Or if there is any RTL connectivity issue or any tie-off issue with the RTL, so that time also we may get this no clock violations. So we need to make sure that all the clocks that we are using in the design are properly declared, properly defined in the SDC file. Otherwise we will see this no clock violations, we will face this error. And also we need to make sure that we are using the latest RTL versions. All the RTL files are latest, and there is a there should not be any connectivity missing in the RTL files. There should not be any mismatch of RTL files. So we need to make sure that everything is proper and latest version, all out of same version, latest version. So if we are facing this no clock violation, means obviously it will affect the timing, right? Automatically it will affect the timing, and it is like whatever we are having a desire to get the result, we are not able to get the result, because all the registers at the end of the day, all the registers should be clocked properly, all the registers should get proper clocks. But if it doesn't get, means it will show no clock violation. So for that, the solution is the only thing that we need to get the correct version of RTL from the design team, and also in SDC file all the clocks that we are using in the design should be properly defined. So to perform to check this no clock violation, we can write this command check underscore timing hyphen include no clock. So it will report if there are any no clock violations in the design after synthesis. Next is unconstrained endpoints. So as we already told, unconstrained endpoints, why we generally see unconstrained endpoints, we can see due to if the clock definitions are not properly defined in the SDC. Another thing is that if the IO constraints are missing or incorrect, that time also we may see these unconstrained endpoints. And if the timing exceptions that we mention in the SDC file, like false path, half cycle path, multi-cycle path, all these informations, if something is incorrect, it will throw this error, unconstrained endpoints. So we need to make sure that we are having proper SDC file with all the informations clearly defined and declared. So so if any IO constraints are missing, means it then automatically the external launch time for the input path or the capture path for the output path will be missed, right? So we can't do that. We need proper IO constraints. So that has to be clearly mentioned in the SDC file. And if the path is expected to be false path, then we need to correctly define it in the SDC. Otherwise it will show like a timing issue will throw, right? So we need to make sure that all the IO constraint, clock definitions, and all the false path related exceptions or any other timing exceptions has to be clearly defined and declared. So the solution is the only thing, the correct constraint file again, and all the IO delay should be properly declared, and every exceptions should be clearly defined. So the command is that we are like using which we are going to see if there are any unconstrained endpoints is check timing hyphen include unconstrained endpoints. Next is timing. So why do we get this timing issue? after synthesis. So the major reasons are due to the previous two checks, unconstrained endpoints or no clock violations, and other than that there can be certain uncertainty issue also. Like we are saying previously, we have seen if there are any incorrect or missing constraint like clock relations or clock exceptions, that can be a reason. Also, if the uncertainty is incorrect, like after synthesis, what we see only the setup time, because by that time the real clock is not there, that time only ideal clock is there. So we are mostly focusing on the setup time only. So setup time means we have to see the setup uncertainty should be properly mentioned in the HDC file. If it is more or less, it will affect the timing. So if there is a huge timing violation after synthesis, means it will again affect all the stages of physical design. That means it's just a wastage of time. So designer can't go with that. So because again if timing issue comes, means again it will affect the power and area. That means PPA can't be properly optimized, PPA wise trade-off can't be properly done. So we need to make sure that uncertainty along with the exception definitions, or along with all the constraint and clock definitions, everything is properly mentioned in the HDC file. And if there are any if we see the tool is not able to make the path groups properly, then user has to define path groups separately. If tool is considering only reach to reach path or any particular path they are considering, then the tool has to the user or the designer has to mention the what all are the required path groups, so that tool can also solve those path groups based timing also. And also if there are any multi-bit banking that we are using after synthesis, that time also we need to disable those multi-bit banking for some time. We can again enable it at after placement stage. And it can sometimes also happen due to this when we are performing physical aware synthesis, we actually expect that our timing will be much better, because after logical synthesis we give the netlist to the physical design team. And when we are getting the knowledge about the macro placement and other initial placement informations with in a def file, so when we are performing that physical aware synthesis, it like tool generally tries to make sure that it improves the timing violations and it is giving a better timing result. And also it is good for better turnaround time also. So we need to make sure these things. And also nowadays, since we are going with the lower technology nodes, we are seeing the timing violations. So tool is all the tools are coming up with certain effort level. So we need to make sure that we are setting this setting up these things like timing efforts at high level, so that a tool can try to optimize it more. Tool focus on the timing more, on the focus path groups, and it tries to do incremental optimization. So for this timing, we are using this command report timing, or we can directly go with report keyword. So in report keyword also it will mention all the timing and everything details. So these are the three main checks that we perform at SDC. Next is netlist check. So if our SDC checks are proper, there are no errors. If our library checks are proper, mostly we can expect that netlist checks in netlist check we will see most of the things are better way most of the time. But still there can be certain other checks also that need to be performed specifically after we generate the netlist. So we are going to see what all those. So if we see here, for netlist check directly, if we want to perform in Innovus, we can perform this command check design hyphen netlist. If we are performing in ICC2, we can use directly check design. So it will give us the netlist related all the, if there are any errors, it will report. If there are no errors, it will report all the result. So the first check that we do soon after getting the netlist is that the LEC. We use another formality, or we use a caliber tool to validate that the netlist is correct based on the RTL. That means the logic wise it is equivalent to the RTL. Whatever get level netlist we are getting, it has the same logic with the RTL. So the logic, we can't compromise with the logic. Logic has to be same. Otherwise, if logic gets disturbed, means totally it's a waste. Totally it's a wastage, right? So we can't compromise there. We have to make sure that logic is properly performed. Logic is properly checked and it is consistent. It is constant. So we basically go with this synthesis LEC. So after synthesis, when we perform, we tell it as pre-layout LEC or synthesis LEC, and it is done between the RTL and the synthesized netlist, and then it is performed on synthesized netlist with the post-scan netlist. So these two things we generally perform after we have the netlist in our hand. So the tools that we use from synopsis, that is formality, from cadence we use conformal. uh, the the reasons why we can see sometimes in LEC, if we are checking for a particular block or a module, if we are seeing if we are performing this LEC, logic equivalence checking, that time we may see that it is showing the result as failed. Why? It can be due to CSN missing, that is connect supply net are properly not defined or properly not connected. So due to that LEC may fail. Otherwise, also if the isolation cell strategy, like in mapping strategy, if it is not properly defined, if there is any issue with the UPF constraint, like in UPF we will mention all the isolation strategies, right? There we will mention the mapping also, mapping of isolation cells also. If there are any different isolation cells or properly it is not mapped, that time also we can see this issue, isolation, we can see this LEC failure issue. And if there are any undriven nets, so why do we get these undriven nets? Undriven nets are basically like this problem basically arises if we are like leaving any if there are any nets which are like not properly driven. Like if whether it's a like, generally there are three types of three types of nets, right? Signal nets, signal net, clock net and power net. So if any of the net is undriven, like it is not driving any of the logic, that is the time we will see this undriven issue, we will see this LEC failure. Like if we have any undriven nets in the RTL itself, if in RTL only properly it is not defined, properly it is not getting the logic, then the synthesis tool will tie off these nets using LEC failure. So this can be resolved if we are getting fixed the RTL, that is we have to talk to the designer and they have to fix this issue in the RTL, and they have to again give us a latest RTL version. And with that only, if the undriven is if we are still expecting the undriven, then we need to use undriven constraints to pass this LEC. So these are the three main reasons why we generally see LEC is failing. And if LEC is failing, means the equivalence is not maintained. That means the logical equivalence is not maintained between the RTL and netlist, and again that means the functionality failure is happening. So that is not expected in the design. So this is the first thing that we go with. Next is timing loops. So we more often hear about this timing loop. So timing loop, we can sometimes hear about combinational loop as well as sequential loop, but mostly we see this timing loop issue in between combinational logic. So like say if in the RTL, if in between any combinational logic the output is again feed into the same input, that means it is creating a feedback loop kind of thing, right? That means it is creating a loop basically. So that loop is basically timing loop. That means we are not getting any endpoint, it is continuously creating a loop, we are not getting any endpoint. So we need to break that. We need that, otherwise we will get a metastable data. We can't expect that what output we are going to get. It is totally metastable, it can give logic 0, logic 1, we can't expect that. So we need to have a endpoint to properly have timing checks. So that's why we need to make sure that there are no timing loops in the design due to any RTL connectivity issue in the design. So otherwise we won't have any endpoints and it will affect the timing. So the solution, as I told, that we need to break such path, and we need to find a endpoint, properly endpoint we need to get. So we need to talk to the designer team again. They have to update in the RTL and they have to share us the latest RTL version. So to perform this timing loop, we can go with this check timing command. Check timing a hyphen include inside bracket loops. This will give us if there are any timing loop issues. Next is empty module. So this is another type of RTL related issue. So generally, if RTL module definitions don't have proper logical content, like if like we know that in RTL all the modules will have input, output, and the word, everything will be declared, right? If any of the things are missing, that means module is not having a proper thing. That means if any logical content is missing, means the module tool won't be considering that module. That means it will show us an empty module. If anything is missing, means that module is not can't be performed during compilation stage. It will be totally excluded. So tool will consider that as an empty module. So generally synthesis time, the tool will optimize them. The tool will remove such modules, and if we want to preserve such empty module, because sometimes what happens, like when designer starts with these RTL creations, by that time physical design people also slowly they started making the constraint files, all the inputs. Slowly they also start working from their side also, like synthesis side also they start working. So sometimes it may happen that designers are still working on creating the modules properly. So you need to talk to the designer team. They need to update that whether they are going to make all the modules properly defined, or whether we need to, like as a designer, whether like as a synthesis engineer, you need to make sure whether you need to keep this empty module for future references. So if they are updating, that means you need to incorporate those latest version of RTL, and then only you will get the module updation. Otherwise empty module is of no use, right? So we need to make sure we are if we have to consider that for later stages, if we want to again go with the next iteration for synthesis, then we can set it as set don't touch. Otherwise we can just remove, like tool will just remove it automatically during compilation stage. So for empty module, if there are any empty module, we can use this command, innovus command, that is check underscore design. So it will report if there are any empty modules also. Next is if there are if the tool is removing any flops, that is we call as removed flops. So generally what happens during compilation stage or during optimization stage, tool sometimes will remove certain flops, certain registers it will remove. And why it will remove? If those registers are found as unloaded or constant value, so that tool will try to optimize them, tool will try to remove them, and during compilation stage only it will be done. So if such flip-flops are expected in the design, again we need to use certain constraints to preserve them. So the command that we generally use are report unloaded registers, report constant registers, and again we need to talk to the design team whether they are going to give any but they are going to update any RTL related to these things, or whether they have any plan related to these things, like they are going to update things. So we need to consult with the design team and we need to get the latest version of RTL. So these are all RTL based related to stuff. So it's not that always synthesize people are making any mistakes. It can, because we are dependent on the RTL also, right? So we need to sometimes consult with the RTL team as well. Next is floating pins, and after that is multi-driven pins. So these two are the major checks that are performed, because these two are more often we see as a error. So in design sometimes we may see that there are certain pins that are left unconnected. So such pins we call as floating pins or floating nets. So while performing this after compilation, when we perform this optimization stage, sometimes tool will optimize such floating pins or nets because it is basically breaking down the logic, right? So that's why it will be generally optimized by the tool. So we need to make sure if we are that we need to make sure that all the pins are properly connected. If there are any floating pins, again we need to talk to the designer team. So basically, for this floating pin information, multi-driven pin information, all these informations you can generate using check design. If in check design you can't get, there are certain TCL script that we have to write out. So with using those TCL script, you can get which all are floating pins in particular area or for the particular block. You can find out using those TCL script. I'll talk about those TCL script later in some other video. Next is multi-driven pins. So these multi-driven pins are mostly reported if the if particular one input is connected to the same net from different modules or different blocks. So if particular one input is connected to the same net, so that time only we see, that means more than one input, sorry, more than one input if it is connected to the same net, that means it is driving multi-driven, right? It is driving more, like one net it is driving more than one input, so it is multi-driven pin. It becomes a multi-driven net or multi-driven pin. So this is also not acceptable in the design, and to fix this we need to again talk to the design team and get the proper correct RTL. Next is latches. So sometimes we get this latches error also. So the latches are not expected in the design, and generally these are again optimized during compilation stage, or if it is not optimized, sometimes tool will stop it. Tool will, sometimes you will see at during compilation stage, tool will stop in between and it will throw an error like the design infers a latch, like that. Sometimes one warning or one error will come. So why this basically why it is not preferred in the design? Because latch, we know these are level triggers and they can be changed, they can change the output at any level of the clock, at an active level of the clock, and the latch output is stable only if only at the inactive level of the clock cycle. So that due to which the entire clock cycle is not utilized for the timing check. So we need to make sure that we are not getting these latches in the design. So like there are certain comment for latches as well. We will generally see it while we are performing synthesis only. We don't need to see after netlist, but still if you are you may get some warnings in the log file, so you need to make sure you are not getting such warning as well, that the tool has inferred any latch. You should not get such warning also. You need to make sure you are checking the log file properly. Next is undriven input port. So as the name suggests, if any input port is unconnected, that time only unconnected means the logic won't be propagated to the, from input the logic won't be propagated, right? That means again the logic is going to be missed. So we can't we can't consider that. So several points in the design might not be constrained by SDC. So we need to make sure that uh, that we are especially whether it's a signal port, clock port or power port, the ports must be connected. We need to make sure this, that if the input port is unconnected means again the logic, we will miss the logic, and we need to verify this port from a synthesis netlist or RTL before leaving them unconnected. The issue generally arises when the intended logic group for these ports does not receive any logic. Therefore, the tool may be able to optimize these logic groups as needed. We need to make sure that there should not be any undriven or unconnected input ports in the design. Whether it's a signal port, clock port or power port, nothing should be unconnected. And same, there should not be any unloaded output port as well, because the output port if like the output port present in the design is not is not connected to any logic through the design means totally we can't load the output. So therefore there will be no output propagating through the output port, right? That means, so we need to check from the again synthesized netlist or RTL that which is the last pin or the element with which this port was connected. We have to fix it. Otherwise the logic the logic about to come through a bunch of logic groups will be missed, totally missed. We can't left out like that. So we need to make sure that there should not be again any unloaded output port. We need to talk to the RTL team, and we need to make sure that things are properly connected, nothing is left unconnected. Next is physical constraint. So we need to see the we need to check the physical constraint as well. So we check this physical constraint, this portion basically last two things, like number 10 and number 11, these two things mostly come during physical aware synthesis stage only. So why do we need to see this physical constraints? So physical constraints means, so we are basically like we need to look at the floor plan objects. So we need to check whether we have all the floor plan related constraints properly used or not. So physical constraints mean placement blockages, routing blockages, all the voltage area creation, physical bounds, etc. All these things should be properly used. If we have proper placement and routing blockages were required, then we are like we are going good. So design will converge, otherwise we will see a lot of issue in the future. So I have personally faced many issues with respect to this. You need to make sure that while you are performing physical aware synthesis, you are not you are properly focusing on these blockages and voltage area creation, and like things are properly used and properly defined. You need to make sure. And sometimes we also see that due to incorrect voltage area being taken in, your placement won't converge well. So again, placement won't converge well means CTS will get affected. So like that, everything will get affected. So you need to make sure that you are using proper physical constraints and you are checking them properly. And like next is legality check. So in legality check, so as the name suggests, we are basically checking that things are properly legalized. So again, this check we do during physical aware synthesis only. So, so we need to make sure that there are no overlapping or orientation related issues. Like sometimes we see macros are overlapped or voltage areas are overlapped. So we need to make sure there are no such overlapping issues or any orientation of macros issues are there in the design. So we need to make sure these issues are properly resolved. And for the basically, if these issues are present means we should fix them before proceeding for the next stage. So we need to basically before performing physical aware synthesis only, we need to make sure at floor plan stage, when we are going for the first time iteration of floor plan stage, we are legalizing everything properly, and then we are getting the first floor plan diff for physical aware synthesis. And if everything is properly done, then we'll go with the keyword check. So first we will never concern about the keyword check, because keyword check is the last list and the last check. So in keyword check mostly we see the timing. The first thing is the timing, setup wise, DRVs wise we see. Then the standard cell count, the area that is occupied by the that is like in synthesis that is expected to be occupied at placement stage. So these things we need to make sure that we are having the we are noting down all this count, and we are seeing that things are proper. Things should not cause any congestion later stages. And power related checks also we do. So these are the main checks that we perform after synthesis before handing over the netlist to the PD team, that is to the physical design team. And if QR wise everything is fine, timing wise, power wise, area wise, everything is fine, then we are ready to go with the netlist, with the optimized get level netlist. So this will give us a better it will also help us to converge in the physical design stages also. So that's all about this video. So thanks for watching this video. If you like the informations, please do hit like, and don't forget to subscribe to this channel if you haven't done yet, and also press the bell icon so that you can immediately get notified when I'll upload my next video. Do comment down below your feedback on this video and share it as much as possible with your friends, colleagues and VLSI aspirants. Follow us on WhatsApp and Facebook channel. Link is shared at the description box. See you next time. Till then, stay tuned, stay safe and keep learning.